geometric questions in differential equations. The talk consists of 3 parts: a summary of classical work, some details of Darboux integrable equations, which have been discussed over the last few years, and then a brief overview of some current developments involving group theoretic methods for studying Darboux integrability. I probably won't get through, this is a pretty ambitious looking program, I probably won't get through all of this, but I did want to try and prepare a PDF file which contained, to the best of my abilities, all the state of the art and what's been done in the past. So we'll do some of these things, and other things you can just look at off of the PDF. We'll focus on the classical problem of integration of scalar PDE in the plane. At the first lecture, we heard a little bit about geometric structures arising from Cartan's 5 variables paper. This is a really very important paper for many reasons. We see some Cartan connections arising. We see a tour de force in terms of the application of the equivalence problem. And the application of the equivalence problem and the Cartan connection have become the dominant aspects of this paper, which most people know a little bit about or a lot about. And what I want to do is sort of remind people today that in the 5 variables paper, it started off with a study of this problem, the integration of PDE in the plane. And what we're going to do is review this problem of integrating PDEs in the plane. And that's the main theme of the talk. And so we're going to be looking at partial differential equations. That's right here. And we'll use the classical notation where P stands for UX, Q stands for UY, R is UXX, S and T, and so on. And we'll be focusing mainly on the parabolic case. This is a case where the characteristics are distinct. They're real and distinct. And leave aside the interesting question of parabolic and elliptic. So we'll focus on this. And I already mentioned that this is part of Cartan's paper. And I want to talk about the fundamental technique for integrating such equations. And the first equation is one that's everyone familiar to, S equals 0, which in terms of this notation is just UXY equals 0. It's a wave equation in no coordinates. And as every student knows, you can write down the general solution for this. And here we mean general in the sense of Cartan-Kähler theorem. If you do the character count for this, you'll see that the general solution should depend upon 2 functions of 1 variable. So we're going to declare a solution to some kind of differential equation, the general solution, if it's got the right function count in it. We'll leave aside questions of whether or not there are singular solutions, which are not included in our formula. I don't think that happens, but it could. Okay, and here's a second example, Louisville's equation, UXY equals e to the u. And many people are familiar that this equation can be integrated in closed form. The formula is more complicated than this one. The interesting difference here is, in this formula here, is that we have an arbitrary function phi, an arbitrary function psi, and their derivatives appear in this formula. And if you get onto Maple and type this in and substitute it into this equation, you get 0. It works perfectly. So that's the general solution.
Syntax error is not
in parenthesis at the end, thank you. And you'll get a syntax error, yeah. And so the kind of questions we want to ask today is, when we have a differential equation of this type, when will we be able to write down a closed form solution? How many derivatives of the arbitrary function appear in that closed form solution? Another example here is this equation, 3RT cubed. which is uxx uyy cubed plus 1 equal to 0. This equation looks much more complicated than this one right here. The solution I just put in for dots because it takes a lot of room to fill up the solution. The solution is not given explicitly as, this should be u. U is some function of x and y. Rather, the solution is given parametrically. That is to say, in these dots there's an arbitrary function of phi. In these dots there's an arbitrary function psi. And z is given by a very complicated expression in terms of those. So it's quite complicated to write down the solution. Geometrically, this equation is quite simple in the sense that when we write down the Cartan structure equations for this in the appropriate frame, this has remarkably simple structure equations, where that one's even has more complicated structure equations. So simplicity in the geometry of differential equations is somewhat in the eye of the beholder. Okay, so this is some of the questions we want to try and address. What are the invariants the geometric invariants that one can associate to a differential equation, which will determine its Darboux integrability? What invariants control the properties of the solution? Okay, so we're going to have a closed form solution, and we'd like to know a priori some information about what that solution looks like. What do the symmetries and conservation laws look like for these equations which are explicitly integrable? Can this method of Darboux, which was originally created just to study this problem, can it be extended to other classes of equations, systems of equations, overdetermined equations, equations in many independent variables or many dependent variables? And as some of you know, I'm very interested in symbolic differential geometry, the implementation of differential geometry in a computer algebra language like Maple. And so the question is, to what extent is this method algorithmic, and that you can put it on a computer and get answers in good order? Okay, so we have a lot of history to cover. It starts off in 1777 with the method of Laplace. This is a very, very beautiful theory, which we'll talk about a little bit. A very good place to learn about the method of Laplace is in Darboux's Theory of Surfaces, volume number 2. Or if your English is better than your French, you can also find a lot of this material in Forsyth's book on the Theory of Differential Equations, volume number 6. So he does a lot, repeats a lot of what's in Darboux. As I was reviewing the history of the subject, I was reading what Darboux had to say on the method of Laplace, and he had a very interesting remark at the end of the chapter. He said there was a very nice paper by Moutard, but unfortunately, Moutard didn't keep an off-site backup copy, and a big manuscript was burned in the fires of 1871 in Paris. There was a civil war in Paris shortly after the Franco-Prussian War, and we lost a lot of important stuff on the method of Laplace, apparently, in that fire. If you use Maple and you type in a Darboux integrable equation in Maple 11, you'll get no solution. But if you type in a Laplace integrable equation in Maple 12, it will produce the solution. So one of the things I'm very interested in is taking these techniques for solving equations and working with the software engineers at Maple to actually make them available to everyone without having to know all the details, of course, of the theory. Some recent generalizations. We've been working on Laplace's method for overdetermined systems. And here's what the theory looks like. So we're going to start off with a linear equation, which I've written in characteristic or null coordinates in this form here. That's not strictly necessary. So this is the equation we have. And the fundamental invariants for this system there's two of them. One's called H, and the other is called K. And so the first thing you do if you have this kind of equation is compute these two invariants. And let's look at the case where h is not equal to 0. Well, then sort of a miracle happens. If one of these equations is not, if h is not equal to 0, then you can make a new change of variables. Z is equal to uy plus au, where a is this u. And now start taking some derivatives of z, and you'll find that z satisfies another second-order hyperbolic equation of exactly the same form. So we can make this change of variables into this equation. We start with this equation, and we end up with this one. And we call this equation the Laplace transform of that equation. Now, you might think that in order to go backwards, that is to say, if you solved this equation, that you'd have to do an integration to reconstruct the solution from this formula. So it looks like to invert this formula, given the solution here, we'd need to do an integration to get back to u. But a miracle happens, and the miracle is that this Laplace transform, which looks like a differential change of variables, is purely algebraic. That if you started with a solution z, you'd work back to the solution u, again algebraically using this transform. So it looks like some kind of Becklin transformation, something taking place on infinite jets. But the method of Laplace is really taking place all on finite dimensional jets. So that's not so clear from the literature, but you can really see it because you have an algebraic inverse. So it's kind of an inverse of a differential operator is another differential operator. So that's quite interesting. Okay, now on the other hand, so that's just h. If h is equal to 0, then you make this transformation and you arrive to this equation. Now that's pretty interesting because this equation is an ODE. So one of two things happens. Either this invariant is not equal to 0, in which case you can transform the equation to something else, or this invariant is equal to 0, in which case you had an ODE to start with and you could just integrate it up. Now, so what happens is the following. You start calculating, you start iterating this process. You start with this equation, you calculate this one. You calculate the Laplace invariant for this one, 0 or non-zero. And you keep doing this process over and over again, and one of two things will happen. You'll calculate these invariants. H is the invariant for the first one. H1 is the invariant for the second one. Hn is the invariant for the nth one. And if these sequences of Laplace invariants terminate at 0, then there's a closed form general solution to the differential equation. Okay? And a famous standard and easy example is this equation right here. uxy equals 2n u over x plus y squared. If you calculate the invariants for this, h0, h1, they all turn out to be just different coefficients times x plus y squared. And if you do go through this process n times, you'll find that hn is 0 and kn is 0. And so you're guaranteed to be able to write down a closed form solution. And here's what it looks like for n equals 3. It's an arbitrary function, whoops, phi, this should be a phi here, phi of x, a derivative of phi, and another derivative of phi. And so that's a kind of, gives you a little bit of an idea of what these closed form solutions look like. Note that under the change of variables, if we make a change of variables, x equals phi of x prime, y equals psi of y prime, and a scaling in u, then these Laplace invariants change by this product of these Jacobians. So these are relative invariants. Okay? So this method of Laplace is a beautiful theory. It's a beautiful introduction to geometric integration theories for differential equations. And really one of the outstanding issues in the subject, I think, is to try and generalize this to broader classes of equations when possible, if possible. Okay, so now we're down to here. The next method that I want to talk about in this historical review of integration methods. It goes by various names, Lagrange and Jacobi, but the important point here is the method of Laplace was a transformation method where we took the equation and we did a transformation to something else, and we hoped that after doing this transformation we end up eventually with an equation which is simpler. This method here is a compatibility, the method of Jacobian-Meyer or Lagrange is a compatibility method. And you see it already in the study of first-order PDE. So here, let's suppose we have this first-order PDE, and we want to write down some solutions to this PDE. Well, the idea is the following. Add a second equation to this. So I start with this. I'm going to add another equation. Now I have two equations here. And we want to, we'll assume that we can solve these two equations algebraically for the first derivatives. And now I arrive to this Frobenius system. And then I'll try and integrate that Frobenius system to obtain a solution. So the question is, given a first-order PDE, can you always find another first-order PDE compatible with the given one? And if you can, then you can integrate this Frobenius system to get a solution to this PDE. So by adding this second equation, you sort of reduce the problem to a Frobenius thing, which is an ODE, and that's what you're going to try and integrate. Okay? The compatibility condition is easy to work out. It's given by some kind of bracket formula called the Jacobi bracket. And so if you write this formula, you'll see that, you'll see that this is a linear PDE for given f. This is a linear PDE for g, so you can always solve it. And so in fact, given an f, you can always find a compatible g. So you can always use this technique as a way of integrating differential equations. And in Jacobian-Meyer, there are various generalizations of this are given. Well, one of the big surprises, let's come back, is that this bracket, which is a bracket ensuring the compatibility of these two equations, one of Lee's fundamental discoveries, and it's described very beautifully in this book by Hawkins on the emergence of Lie theory, is that the Jacobi bracket actually can be identified with a Lie bracket of contact vector fields. So Lee's fundamental discovery, which really led to the emergence of Lie groups, was his realization that this compatibility theory was actually a symmetry theory. So that finding a compatible equation was somehow equivalent to finding a contact symmetry for the first. And so this is one of the themes that I want to illustrate in this talk, is the surprise that Lie group methods show up in the integration theory of differential equations in surprising ways, in ways that you might not have anticipated. I'm having a hard time with okay, so coming to the other theme that I wanted to talk about, unlike the Laplace method, which was very amenable to implementation on the computer, our first attempts at implementing the Jacobi method were not so successful. So sometimes classical methods, which look great on paper, don't actually work so well when you try and do a concrete implementation of them on the computer. There's a series of beautiful papers by Krugloff and Leshagin generalizing this Jacobi method. It's called multi-bracket formalism. And so they have a very general method of determining when an arbitrary given system of equations has some other equations which are compatible with it. Okay, so now I'll just talk briefly about the method of Ampere. Now we're coming back to second-order equations. So we'll have a single second-order equation. And it seems to me, just kind of in my quick historical study of the situation, is that Ampere was one of the first to formalize this idea of an intermediate integral. So we're given a second-order differential equation, and we want to ask, is there a first-order partial differential equation compatible with that one? That is to say, when we differentiate this equation, we get back into when we differentiate this, we get equations which are we'll have another second-order system, and we want these two to be compatible. In the classical literature, they go to great pains to give a variety of names to these intermediate integrals. If it involves a certain number of arbitrary functions, it's called complete. If it involves arbitrary constants, it's called complete. If it involves an arbitrary function, it's called general. Okay, and here's a simple example. This equation, uxy minus uuy, well, it's a pretty easy example. You can just see that this side is a y derivative. It's the derivative. If I differentiate this with respect to y, I get the equation. And so this equation forces this first order expression to be just a function of x. And so this here would be a first order intermediate integral. And since it involves an arbitrary function of x, we would call it general. And so I've reduced, and now when I integrate this, if I integrate this first order PDE, I know the solution to that first order PDE will involve an arbitrary function of y. And so I've reduced the integration of this second order PDE to the integration of this first order one. And so that's an application of first order intermediate integrals a la Monge.
Just a silly question. Do you want half?
Whoop. Yeah.
Okay, sorry for
Yeah, it should be a half here. Thanks. Okay, so lots of typos. Okay, here's another example of a equation. And here's an example of a second order PDE. And here's a complete intermediate integral. So it's a function of u, x, and y. And that would give me a complete first order integral. Okay, so now on to this method of Darboux. The method of Darboux is really the accumulation of all these methods. It includes the method of Laplace. It includes the method of Jacobi. And again, it's a compatibility method. We're going to take our original partial differential equation right here and add more equations to it to get something which is Frobenius. And then we'll say, okay, we've reduced the integration of this partial differential equation to the integration of ODEs. And geometrically, then we would say a hyperbolic partial differential equation in the plane defines a rank 3 Pfaffian system, so a system defined by 3 one-forms on a 7 manifold, 1, 2, 3, 4. I've got 8 variables here with 1 constraint, so I'm on a 7 manifold. And the structure equations for any parabolic PDE can be made to look like this. That is to say, I can complete these 3 forms, theta 0, theta 1, theta 2, to a coframe by adding forms pi 1, pi 2, sigma 1, and sigma 2, such that the structure equations look like this. And we're going to come back later on, way down here, and talk about decomposable differential systems. And you can see that in some sense, this system here is decomposable. The additional forms we added in only occur in the differential of 1. The other 2 forms that we needed to make a coframe only appear in the differential of our other form. Okay, so associated to any hyperbolic PDE, there are additional Pfaffian systems that you get by taking the 3 original forms you started with, theta 0, theta 1, and theta 2, and you can add in these 2 forms, pi 1 and pi 2, to get one characteristic system, or you can add in sigma 1 and sigma 2 to get another characteristic system. And this is rather confusing. Some people call these the singular Pfaffian systems associated to this. Some people call them the Monge Pfaffian systems associated to this PDE. Some other people call them, Brian and Griffiths call these systems the characteristic Pfaffian systems. And I think you all know in mathematics, the more names the same object has, the more important it tends to be. It means it's been rediscovered by people over and over again. So in some sense, these two associated Pfaffian systems are actually in many ways more important than the original Pfaffian system you started with. Okay, so here are these 2 characteristic systems, V1 and V2, and a partial differential equation is said to be Darboux integrable if there are 2 functions, I1 and I2, whose differentials are in the span of those. So we would say that I1 and I2 are first integrals for the characteristic system. And we also need to find 2 functions or 2 first integrals for the second characteristic system. Here's the dual formulation. So we've seen a lot of discussion about geometric structures in terms of distributions. Here I put here the dual distribution. So the dual to the original three forms, theta 0, theta 1, theta 2, would be a rank 4 distribution delta. And the hyperbolicity says this rank 4 distribution splits into a direct sum of two-dimensional distributions, each one with dimension 2. The structure equations say that the bracket of H1 and H2 is back in delta. This is tangent space generating, so if we bracket all of this stuff up, we'll get the full space. And the difference between Darboux integrability and some of the other conditions we saw on these distributions in earlier talks is that here I'm going to require that the derived flag of this not fill up the whole space but stabilize at dimension 5. If this stabilizes at dimension 5, it guarantees this has at least two first integrals. And the other one, this derived flag must stabilize at dimension less than 5, and that ensures that I have two first integrals here. And the standard example, the example that everyone looks at as the canonical example of Darboux integrable system, is the Louisville system. And you can calculate these first integrals I1 and I2 to be x, and uxx minus a half p squared y, and t minus 1/2 q squared. Now, once you've calculated these first integrals, you form the following Frobenius system. You set this first integral to be a function of this, with an arbitrary function. You set this integral to be a function of y, and now you take these two equations together with your original, and now you've got a total system of differential equations. This is uxx, this is uxy, this is uyy. So all second derivatives. So you now have a Frobenius system. The fact that these were intermediate integrals for the characteristic systems ensures that this system is compatible. So I started with this equation, and I created a compatible system of three equations with two arbitrary functions in them, psi, phi, and psi. So it's a Frobenius system with enough arbitrary functions to give the general solution to the Louisville equation. So in summary then, there's two... before we go there, it may be necessary... So this example here, the equation was a second order equation, and the integrals, the intermediate integrals that we constructed were of second order. It may be necessary to prolong the differential equation to very high order in order to find these intermediate integrals. So it's a historical term that we call these things intermediate integrals. Even though they might not be intermediate in any sense, they may have higher derivative order than the equation that you started with. And so in order to study and do research on the method of Darboux, as soon as you realize that it's going to be necessary to prolong the differential equation to very high order, you're going to need some computer software to really help you study complicated examples, because you may have to differentiate the equation to very high order and calculate these invariants at very high order. So it's not uncommon. I have examples where I had to prolong 4 or 5 times. I was looking for Darboux integrability on a 27 or 28 dimensional manifold, so you're at very high dimensional spaces, and then to calculate these invariants in quite a bit of work, but you just hit the button with Maple and it will almost always calculate these for you. So calculating, we should assume as a practical matter that we can always, well, it's clear by just linear algebra techniques that we can get the right count on these, and so integrating to find these invariants almost never a problem. So you can take that as a given. So 2 integrations are required to solve a system of differential equations by the method of Darboux. 1, you have to find these intermediate integrals. That's an easy integration. It's an overdetermined linear problem, no problem. The other integration you have to do is integrate this Frobenius system. And that can be quite difficult. So you're integrating a Frobenius system with arbitrary functions in it. That can be quite difficult to do. Okay, so the new method that I want to discuss with you down here completely avoids this difficult part, integrating this Pfaffian system. Well, it seems like I'm going to change topics completely now and talk about something else that has nothing to do with PDEs, but in fact is very, very essential to the story that I want to tell. It's this idea of Lie equations. So we've been looking at some classical integration methods, the Laplace method for integrating PDE, the Jacobi method for integrating first-order equations, Ampere and Darboux's method for integrating PDE in the plane. And now for some reason I'm going to change and start talking about Lie equations, which is the integration of ODEs. And Lie asked the following question: when does a system of first-order ODE admit a superposition formula? And by superposition formula, first think of the linear case, where if you have a linear system of equations, all our students know that if you have a linear system of first-order equations for n unknown functions, if you write down n solutions, then you can write down the general solution by taking a linear combination of the solutions you found. And so we would call that a linear superposition formula. And quite remarkably, there are nonlinear superposition formulas. And that is to say, there are examples of differential equations or first-order ODE for which the general solution can be expressed as a combination of a finite number of particular solutions with the right number of constants. We already talked about linear equations, and here's a famous example called the Riccati equation. And the Riccati equation has the property that if you know 1, 2, 3, 4 solutions, so x1, x2, x3, x4 are all different solutions, and you take this cross ratio, differentiate it with respect to t, substitute from the equation, you get 0. So this cross ratio is always constant. Well, if you think about that, what that means is if you know 1, 2, 3 solutions, solve this for the fourth, you now have the general solution. So the Riccati equations admit a nonlinear superposition formula. If you know 3 solutions, then you know explicitly the general solution. So, So the question we want to ask is the following: when does a system of ODEs admit a superposition formula? And the answer is total surprise to me. I never quite understood how this comes to be. And the answer is when the right-hand side of the differential equation, so my differential equation was this one right here, when the right-hand side of my differential equation is a time-dependent multiple of a set of vector fields which don't involve time, and those vector fields form a Lie algebra. So we ask the following question: when does a system of ODEs admit a closed-form general solution? That question has nothing to do with Lie algebras, has nothing to do with group actions, but the answer is again given group theoretically. And so here's an example. Let me take my Riccati equation, a of t plus b of t plus c of t x squared, and turn that into a vector field. So I'll put in a partial d by dx and just rearrange the terms here. So I've got a times partial x plus b of t times x partial x plus c of t times x squared partial x. And so the right-hand side of my Riccati equation is in fact a time-dependent combination of 3 x vector fields, and it's partial x, x partial x, x squared partial x. And so the Riccati equation is a Lie equation for the group SL2. Now, you can actually solve Lie equations in the following way. You take the ODE. These vector fields are vector fields on a manifold M. They're not pointwise linearly independent. Certainly on the line, all 3 of my vector fields are independent. And what I'm going to do is I'm going to replace these vector fields X by the left invariant vector fields up on a group, or for the group defined by this Lie algebra. So I can take this Riccati equation on the line and actually lift it up and get an ODE into the group SL2. If this group is solvable, then you can always integrate by quadratures the group up on the group manifold and then project back down to get your solution. This is an effective method. I've been working very hard to implement it in Maple, and in due time we will have an implementation of Lie's equations for solving ODEs by this Lie's method. There's no problem in theory with the implementation. The problem is to get it to run fast enough. There's a lot of calculation that's got to be done, and you can't. The rule is if you hit the button, you have to have an answer in 10 seconds or less, or people lose interest. So you really need to have efficient and fast methods when you want to integrate them. Okay. So summary. We had three kinds of different ideas arriving in this classical literature. One of them was a transformation method. We see that in the method of Laplace. The other one was, you go by many names, it's a reduction in the number of variables, it's a restriction by adding new equations, it's compatibility by adding new equations, or maybe you can think of it as by quotienting. But this is Jacobi-Ampere method, all involves compatibility equations, increasing the number of equations to get to something of finite type, integrating the finite type system. And then the third one is very, very interesting. This idea of Lie equations is you started with a system on some small space, might be very difficult to solve. You lift it up to some bigger space with more variables. And on that bigger space, you might be able to triangularize the system. You might be able to separate variables. You might be able to do all kinds of techniques for integrating on the bigger space that you weren't able to do on the smaller space. So this is a very, very interesting idea for integrating equations. The other point I wanted to make was Lie groups make unexpected appearances. So if you read a book, for example, Peter Oliver's excellent text on Lie group methods in differential equations, those are all symmetry group methods. You calculate the symmetry group of a differential equation and use that symmetry group to draw inferences about the solution space and how to find solutions. The Lie groups that are appearing in this Lie equations, for example, are not symmetry groups of the equation. So it's something very different. And then not all integration methods are necessarily appropriate for computer algebra systems. Well, I'm almost only here, but I want to make a final conclusion. And then if we have a little bit more time, we'll come down and talk about some of the details. Okay, so the method of Darboux evolved over a 100-year period as a generalization of Jacobi, Meyer, and Ampere's method for the construction of intermediate integrals. The subject more or less came to a standstill with the publication of Goursat's famous book on partial differential equations in the plane, until 1939, 1940, when Vassiot made a very fundamental discovery. He discovered that, let me see if I can go back a bit here. He discovered that whenever you're studying the method of Darboux, you have to write down these invariants, no problem there. Then you have to integrate this Frobenius system. And he discovered that integrating this Frobenius system always led to equations of Lie type. So that's why I talked about Lie equations in this discussion of the method of Darboux. The final step, for some miraculous reason, always involves the integration of equations of Lie type. So in this method of Darboux, given a Darboux integral equation, buried deep inside it is a group, which we call the Vassiot group. And following Vassiot, Mark Feltz, Peter Vasilio, and I have reformulated the method of Darboux in terms of Lie groups, Lie equations, and this lifting idea, where we take our partial differential equation in some variables, we lift it up to a bigger system, that bigger system very easy to integrate, and then integrate the bigger system and project back down. So we can reinterpret this whole business of the method of Darboux in terms of Lie groups, Lie and Lie equations. Okay, and then this new approach has many, many applications, which I'll discuss briefly now. Okay, so let's see. What time do we stop at? 10 to. It's 15 minutes.
10 minutes.
10 minutes. Perfect. Okay, so in the second part of the talk, I just wanted to mention briefly some of the work that's been done on calculation of symmetries, conservation laws, and classification for Darboux systems. I'm just going to go very quickly through this. Actually, I want to come down to here. Let me just come down to here and just make one remark. This linearization trick that Boris talked about. So if we have a partial differential equation in the plane, we can compute, I've got some typos here, we can compute its formal linearization. So just take a one parameter family of functions, differentiate this equation, you'll get a linear equation. This should be rho xx, this should be rho yy, sorry about that. And you get this linear equation. You'll get this linear equation. And there's many ways to think about this. If you're an applied mathematician, you think about linearizing against a fixed solution. But from a geometric point of view, I want to think of this linear equation as being defined on the equation manifold of the original equation. So it's an equation built on top of the equation manifold that I started with. Now, we can clean this linearization up a little bit. Assuming that this equation is hyperbolic, I can always find two vector fields x and y such that this linear equation, the linearization of this nonlinear equation, looks like this. This is what I had on the first slide. This is an equation susceptible to the techniques of Laplace, where we can do Laplace transforms and so on. Now at this point, the method of Laplace is sort of very concrete. At this level here, we're just going to look at what Laplace did and interpret everything rather at the symbolic level. So you can calculate now, for this equation, a sequence of invariants. And it turns out that this sequence of invariants that you get from the method of Laplace are actually contact invariants for the original equation. So whenever you have a nonlinear problem, a very good idea is to try and look at the corresponding linear problem. If you calculate the invariants for that linear problem, they'll almost always give you invariants for the nonlinear problem. Kind of a very interesting thing. Now, we were able to prove that this sequence of generalized Laplace invariants terminates at 0 precisely when this nonlinear equation is Darboux integrable. So linear equations, Laplace invariants terminate, integrable. Nonlinear equation, generalized Laplace invariants. This sequence of generalized Laplace invariants terminates, the equation is Darboux integrable. These equations, these invariants, control just about every property of this equation you can imagine. You're able to construct higher order symmetries, higher order conservation laws, exactly when these invariants, one of them or both of them, vanish. So let me go forward now, and in the last 5 minutes, just talk about the most recent work.
Just a question. These vector fields x and y, they are on which space?
You should, good question. You should think of them as total vector fields. So it's a total derivative with respect to x, total derivative with respect to y. And you should think of them being prolonged up to the infinite jet space. But they only act on finite dimensional objects at each step. So these were total derivative vector fields. Is that okay? Mm-hmm. Yeah. Okay.
I also want to know Frobenius type, PD of Frobenius type,
Mm-hmm.
and And also, what do you mean by generalized solution? Can it be?
Sure, maybe we'll come back and just talk about that
Okay.
in a minute, okay? So I just want to end now with our most recent work. So I'm going to call now a Foffian system I, defined on some manifold, decomposable if there's a very colorful coframe. So I take the thetas and I split them into red thetas, blue thetas, and green thetas, and I complete that to a coframe with red pies and blue pies, such that the structure equations look like structure equations for a hyperbolic system. So the green ones are in the so-called derived flag. So we don't. Their exterior derivative is 0 modulo everything, and then the red thetas differentiate into the red pies, and the blue thetas differentiate into the blue pies. This is exactly what we had in the classical case, where we had one red pie and one red theta and one blue theta. Now it doesn't matter how many, and we can associate to this, just as we did before, these singular Foffian systems, and we'll declare the system to be Darboux integrable if this and this have a lot of first integrals. How many? Well, there's the exact count. The derived flag for the red V plus the blue V has to equal the full space, and likewise the other way around. So this is a huge generalization of the classical notion of Darboux integrability. It includes systems of PDEs, it includes overdetermined PDEs, it includes lots and lots of different things. And the only assumptions you have to make are that the structure equations look like this, and the derived flags look like derived flags satisfy this. I leave it as an exercise for you to say a system is Darboux integrable if it's a distribution and the different distribution splits into H1 and H2, and then you can write down from this simple conditions on the distribution. Okay, here's a way to construct Darboux integrable systems. Take a Foffian system on a manifold M, a red one, and another Foffian system on a manifold M. Let G be a common symmetry group. So G is a symmetry group for this Foffian system and this Foffian system. Step 1, form the sum. So take these two Foffian systems and add them together to make a Foffian system on this product. G was a group acting on red M and on blue M. Let G act diagonally on the product. Calculate the quotient differential system. So that is to say, look at the forms in here, which are pullbacks under the quotient map to this quotient. Okay, and then theorem. This system that you get by starting with two arbitrary differential systems and forming this quotient will always be Darboux integrable. So this is the fundamental fact number 1. For 100 years, it was very difficult to write down Darboux integrable systems. And now we have a completely general group theoretic method which will allow you to write down Darboux integrable systems at will. How many? Well, as many Darboux, you can write down as many Darboux integrable systems as you can write down differential systems with symmetry. And oops, I teched this up late at night. I wonder what happened to my backslash. Okay, so start with two principal bundles. Here's an example. A very special case of this showed up in a paper by Toro. So let P, red P and blue B be two principal bundles with connection 1 forms omega I and omega I. Just take the difference. This difference will be basic with respect to the action. It drops to the quotient, and it will always define for you a Darboux integrable system. Okay? And now, the big miracle. All Darboux systems that come from this form. Okay? They're always quotients of something. And I can tell you what the group is, and I can tell you what they're quotients of. Okay? Coming back to, if we come back to this definition of Darboux integrable systems, I want you to think of taking the dual picture. So this would be delta is equal h1 plus h2. It would satisfy certain conditions. What I'm saying is I have a complete closed local normal form for all such distributions. And it's convenient to describe that normal form in terms of this quotient theory. Okay. So conclusions, final conclusions. All questions about the method of Darboux now translate into questions about Foffian systems with symmetry. It's a story about transformation groups. This new approach is much better for computer algebra system. It allows me to integrate broad classes of differential equations which were inaccessible before. It leads to new and very general classification results. You get a complete solution to the equivalence problem for Darboux integrable equations. You get a deeper understanding of the Cauchy problem for Darboux integrable systems. You can construct Becklin transformations effortlessly with this technology. So it really, I think, takes the study of Darboux integrable equations to a completely different level that was inaccessible to us just a few years ago. Okay, sorry I went a little bit over time. Thank you very, very much.
Any question or comment?
For single equations,
Yes.